I'm looking at exercise 16 from section 1.7, and I'm trying to prove an if-then statement. So this one steps it up a little bit. It looks like we don't have just two atomic propositions attached by an implication, but we also have this or in here to deal with. So we do have, two propositions, m, n is even, and m is even or n is even, but within our conclusion we have a little bit more stuff going on than we might have in previous proofs so far. So there's different ways to prove this, right? You should have seen in the section that there are several ways to prove implications. And so what I've done here is just outlined a few different methods for this particular statement. So if we were to do a direct proof of this if-then statement, we'd start by assuming the hypothesis. So we'd assume m times n is even and prove that that means that m is even or n is even. And we could do that. We could totally do that proof. And we could do a proof by contraposition. We'd assume the negation of the conclusion. Okay, and now the negation of this conclusion is kind of tricky to wrap your head around. The conclusion of this implication is m is even or n is even. So let me try to represent this symbolically, okay? So let's let m be the statement that, well, really it's a predicate, right? So p of m, let's say that means m is even. And then let's say p of, well, let's say, yeah, we can just define p of m is even. So what we're trying to prove is for all integers m and n, we want to show that if mn is even, then m is even or n is even. So if we want to do this proof by contraposition, remember the contraposition of this statement would be, we leave our quantifiers alone. The contraposition of this statement is the negation of the conclusion implies the negation of the hypothesis. Okay? So now we just want to kind of come out of our symbolic world here and see if we can understand what those negations mean, right? So if we negate p of m, so I want the opposite meaning. So if p of m is true, then not p of m should be false. So if m is even, the opposite would be m is odd. Okay? So let's keep that in mind. Another thing when we try to figure out this contrapositive symbolically, we want to think about De Morgan's, right? Because if we negate an or statement, it becomes the negation. Here, let me rewrite this out, expand it a little bit more. If we negate an or statement, we will have to negate both pieces that are joined by or, and then it changes to an and. Okay, so now we can think about our contrapositive a little bit more clearly, and we can write this out. So let's write out and see what we've got going on here. So this means for all integers m and n, if m is odd and n, so m is odd and n is odd, then m times n is odd. Now, I don't know if you can see it, but this seems a little bit more straightforward to prove, because all I have to show pretty much is that the product of two odd integers is an odd integer. And I already kind of know that, and I can just do that directly 2k plus 1 times 2l plus 1, we get 2 times some integer plus 1. So that's proof by contraposition. Proof by contradiction isn't a bad option either. Well, with proof by contradiction, you're going to be assuming the negation of your statement. So then you have to go back and remember what the negation of an implication is. So with proof by contradiction, if you're trying to prove some statement, P implies Q, let's say here, let's kind of go back to a smaller example. If we're trying to assume the negation of this, remember the negation of an implication is the negation, right? Our material implication here, and then apply to Morgan's. So if we want to do a proof by contradiction, we'll assume our hypothesis and the negation of our conclusion. So if we want to do a proof by contradiction here, we'd assume that m plus n is even and negation of my conclusion, which is m is odd and n is odd. So we'd assume all this at once. Okay, this is different than the direct proof and contraposition, because with direct proof and contraposition, we're assuming only one thing about our hypothesis or our conclusion. With proof by contradiction, we negate the whole thing and assume that's true. Okay, so what I want to do here is actually do each of these methods so that you can see that there are indeed different ways to approach this proof, and hopefully you can see that there is one that is, I think, more efficient, but it doesn't have to necessarily be the only way. Okay, so in this video I'm going to start with the proof by contraposition, and that's just because I think that's the one that is most easy to understand, and so I'm just going to start there. So what I'm going to do here is actually just prove the contrapositive of the statement. So like we talked about just a bit ago, the contrapositive would be that if n is odd and m is odd, then m times n is odd. So let me just kind of set it up for you and talk you through my little background info here. Okay, so I'm going to assume m, n odd, okay, and then I'll use the definition of odd integers. That's pretty much whenever you assume something's odd or even, you're going to rewrite those integers based on the definition of even or odd integers, right? So I'm going to use definition of odd integers here. And that's a lot of what we're doing in this section. We're just applying the definitions of even and odd integers, or we're applying definitions of rational and irrational numbers, using some different properties of integers and real numbers, and doing some algebraic manipulation, okay? And then, once we rewrite that m and n, let's look at the product and see what that gives us. And we're going to see, when we do some algebraic manipulation here, now careful, this is not 4kl plus 1, right? We've got to think about our distributive property here. And we have to distribute everything in the left-hand side term to the right-hand side term, and vice versa, right? So we actually get 4 terms. Okay, but this looks funny, but we still have, this is an even number, plus 1, right? And that's all we need, 2 times some integer plus 1. So 2 times 2kl plus k plus l plus 1, right? 2 times some integer plus 1. So we've written it in the form of an odd integer. And that's it. We've proven the statement. Not too bad. But this is not a very nice way of presenting our proof, right? It's not very readable. I don't really know what k and l and m and n are, right? It's not well explained. So let's go ahead and write this out in a way that's a little bit more clear. And it's nice when you're proving a statement using contraposition to let your reader know that you're trying to prove the contrapositive. So you can say or let's start by declaring our variables, right? It doesn't always flow perfectly the first time. So we're going to start with just letting m and n be integers. Let m, n be integers. For the purpose of proof by contraposition, assume m is odd, is an odd integer, kind of redundant, and n is an odd integer. Okay, so this just tells your reader, okay, she is assuming the negation of the conclusion. So I know that my hypothesis in the actual statement I'm trying to prove is not m is odd and n is odd, an odd integer. Crap. Okay, and then I'm going to apply that definition, right? Then, by definition of odd integers, m equals 2k plus 1 and n equals 2l plus 1. I got to use a different integer here. I can't use k again because I'm not assuming that m and n are equal. That's more than we know. And I've got to be clear to my reader where k and l are integers. I need to declare my variables. Okay, now I'm going to take the product of them, right? I'm trying to get to the conclusion that m times n is odd. So I probably want to see what I know about m times n now that I've found out more about m and n. So note, m times n is equal to 2k plus 1 times 2l plus 1, which is equal to, we did this algebra in our background work, oops, 2kl plus l plus k plus 1. Since k, l, and 2 are integers, m times n is 2 times some integer plus 1. Hence, by definition of odd integers, m times n is odd. Okay, I could stop it here, right? I've got a clear conclusion, clear hypothesis, okay? And I can see what statement's been proved. There's no gaps, all variables have been defined, all steps are clearly defined, so my proof is airtight. However, you know, I could go on and state that, okay, thus by contraposition, if m times n is even, then m is even, or n is even. But as long as your hypothesis and conclusion are clear, and the reader can see without looking at the statement before what you have proven, you're good to go. So come back in the next video and I'll go through and do, let's see, I think I'll do a proof by contradiction next.